Skew bridge analysis using ANSYS. Abstract. This research is all about, for the analyses of skew bridges by the finite element method using 8-knotted isoperimetric brick element, serendipity, shell elements, and some different elements are also attempted, and has seen that brick elements give better results for shear. ANSYS software, version 7, has been used for the finite element analysis. The modeling which is done is applicable for any skew angle and aspect ratio of slab bridges. In this analysis, different types of I.R.C. loadings, Class AA tract and Class A, have been built in the modeling, and also variable live load positions have been considered, to obtain maximum stresses development on the slab. The parametric study and detailed analysis has given a useful understanding for analysis of skew bridges. The main parameters considered were angle of skew, width of bridge and span length. Based on this investigation, certain rules for fast examination of skew slab bridges have been suggested in the ANSYS. The consequences of this examination are valuable for configuration engineers working in the investigation of skew slab bridges. Keywords: bending stress, torsional moment, ANSYS skew slab principal bending moment, principal moment torsional. Introduction. 1.1 General. Skew bridge is characterized by skewed angle, which can be defined as the angle between the normal to the center line of the bridge and the center line of the abutment. A skew bridge is also defined as bridge whose longitudinal axis forms an acute angle with the abutment. The arrangement of such a structure is meet several requirements, which includes man-made obstacles, space limitations, or mountainous terrains, complex intersections, etc. Many bridge decks fabricated today have some type of skew, curve or taper. For current long vehicles and substantial traffic, it is desirable over half straight carriageway at that point to arrange the level bends. In order to optimize the requirements of high speed and safety measures of highway traffic, as well as to reduce the initial investment in the long curved approach roads, it became most important to minimize the number of horizontal curves in the modern highway alignments. This requires for the construction of skew bridges at such all locations where crossings are not orthogonally. In hilly area, skew bridges are most common because road alignment cannot be changed due to topographic conditions. Other cases can also be considered, like road crossings and railway, which are never orthogonal. In USA, nearly 40% of the total bridge deck area is on skew alignment, and approximately 10% of the total area is on heavy skews that ranging between 40 degrees to 70 degrees. In India, present trend is toward the provision for skew bridges in order to optimize the functional requirements as well as to minimize the cost of project. The presence of skew makes the design and analysis of bridges more difficult as compared to that of right bridge, and also has a considerable effect on the structural behavior of decks and on the critical design stresses. The effect of skew in simply supported bridges can be ignore up to 15 degrees of skew, and the bridge can be designed as a right-angled bridge. However, the effect of skew becomes significant at lower skew angles in integrated bridges and continuous decks, particularly in regions of intermediate supports. 1.2 Objective of this research paper. The main purpose of this research is to develop FEM model using software ANSYS for analysis of skew slab bridges for various I.R.C. loading conditions, and to analyze a single lane, double lane, and 4-lane skew slab bridges for various spans, from 6.0 m to 10.0 m span, and for various skew angles, from 0 degrees to 60 degrees, and to obtain the final design forces. 1.3 Finite element method. General. For any structural stress analysis problems, the major objective is to determine stresses and displacement throughout the structure, which is in equilibrium and is subjected to applied loads. For many structures, it is difficult to determine the distribution of deformation using conventional methods, and thus the finite element method is necessarily used. The basic idea behind finite element method is to obtain the solution of complicated problems by replacing it by their individual elements or component whose behavior is readily understood. These elements are interconnected at specified joints or nodal points which possess an appropriate number of degree of freedom. Steps involved in finite element method analysis. The solution of general static continuum problem by the FEM always follows step-by-step process. 1. Discretizations and selection of element type. This step involves dividing the body into an equivalent system of finite elements with associated nodes and choosing the most appropriate element type. 2. Selection of displacement function. 1.4 Element geometry. After discretizing the structure, the next step is to choose proper displacement function. The approximate displacement function within the geometry of element can be given by a simple function in terms of the nodal value of that element. This function is known as shape function. The element geometry in terms of x, y, z, coordinate of a point is expressed in term of nodal coordinates as follows. Where 11, y, zi are the coordinate of node I. Ni, shape function of node I. N, number of nodes in the element. Generally for the two-dimensional problem rectangle, triangle, and quadrilaterals geometric shape elements are used, which may have straight or curved sides. For the 3D problems tetrahedron, hexahedron, and parallel element are used. Over each type of elements there will be several nodal points, differing in number and location according to the element type. It is obvious and important to note that on nodal point values of the problem variables must be same in the connecting elements. Most commonly elements used for the stress analysis are tabulated in Table 3.1. 1.4 Type of element used. SOLID 7.3 is used for the three-dimensional modeling of solid structures. The element is defined by 8 nodes having 6 degrees of freedom at each node, translations in the nodal x, y, and z directions and rotations about the nodal x, y, and z axes. 1.5 Validation of results and selection of elements type. For the modeling of slab bridge following elements were taken and the results were verified with conventional analysis. This was done to select one particular element which is most suited for study. The test problem taken is a 15 m wide slab of span 10 meters simply supported at both the ends. The material is taken as isotropic concrete with following properties. E. Modulus of elasticity, equals 28,000 N/mm2, M30 grade concrete. V. Poisson's ratio, equals 0.152. P. Density of concrete, equals 0.00025 kg/mm3. The bridge was analyzed for the self-weight only. Types of elements used as per ANSYS Element Library: Solid 45, Shell 63, Sold 73, SOLID 186. SHELL 63 has both bending and membrane capabilities, both in plane and normal loads are permitted. At each node the element has 6 degrees of freedom and translations in the nodal x, y, and z directions and rotations about the nodal x, y, and z axes. Stress stiffening and large deflection capabilities are included. A consistent tangent stiffness matrix option is available for use in large deflection, finite rotation, analyses. SOLID 186 is a higher order 3D 20-node structural solid element. It has quadratic displacement behavior and is well suited to modeling irregular meshes. The element is defined by 20 nodes having 3 degrees of freedom per node, translations in the nodal x, y, and z directions. SOLID 186 may have any spatial orientation. The element supports plasticity, hyperelasticity, creep, stress stiffening, large deflection, and large strain capabilities. It also has mixed formulation capability for simulating deformations of nearly incompressible elastoplastic materials, and fully incompressible hyperelastic materials. SOLID 45 is used for the three-dimensional modeling of solid structures. These elements are defined by 8 nodes having 3 degrees of freedom at each node, translations in the nodal x, y, and z directions. The elements have plasticity, creep, swelling, stress stiffening, large deflection, and large strain capabilities. The analysis cannot capture the bending behavior with a single layer of elements, for example, in the case of a fixed-end cantilever with a lateral point load, modeled by one layer of elements laterally. Instead, 4 elements are usually recommended. The slab was meshed with element size of 500 x 500 mm. The number of solid elements across depth is 8 layered. The results found out are given below. The major bending stress along the span comes out to be 2.072 N/mm2, the shear stress along the supports comes out to be 1.66 N/mm2. As seen from the graph below, nearly all the elements are giving the same results. However, the shear stress is found to be highly distorted for elements other than SOLID 73. 1.6 parameters considered. 3 different lane bridges, single lane, 5 m wide, double lane, 12 m wide, and 4 lane, 19 m wide, were taken in this study. The width of bridges taken was equal to the full formation width of the road for 2 and 4 lane bridges as per I.R.C. guidelines. Following assumptions were made to make the analysis simpler. 1. Reinforced concrete has been taken as isotropic with the following material properties. Modulus of elasticity equals 28,000 N/mm2, Poisson's ratio equals 0.152, density of concrete equals 0.000025 kg/mm3. 2. The curb have not been considered integrated with slab, but have been replaced by equivalent self-weight acting on the slab. The height and depth of the curbs is as per I.R.C. guidelines. 3. The modeling analysis of the slab has been done using SOLID 73 with 8 layers across depth and size of 500 x 500 mm. 4. The support have been kept as simply supported, and for that the translation of the middle layer nodes has been restrained in the y direction only. However, to restrict secondary movements, the nodes at the other support has been restrained in z and x translations also. 1.7 Geometry of bridge model. 1. The 2 lane bridges having different spans of 6 m, 8 m, and 10 m were taken. The width of the bridges were taken as the full formation width of 10 m. The side curbs were taken as of 0.4 m wide and of 0.25 m depth. The thickness of bridge were taken as uniform depth of 0.6 m for 6 m span, 0.75 m for 8 m span and 0.9 m for 10 m span. Each span was distributed into 0 degrees, 15 degrees, 30 degrees, 45 degrees, and 60 degrees skew that causes total 15 models of 2-lane bridges were made. The meshing was done by using SOLID 73 element. 8 element layers were taken across the depth and 24 elements were taken across the width. The element number along the spans were 12 elements for 6 m span, 16 for 8 m span and 20 for 10 m span. Hence for the skew bridges the element shapes were parallelogram and for right bridges they were square. 2. For single lane bridge only 8 m span was taken and 5 different skew angles 0 degrees, 15 degrees, 30 degrees, 45 degrees, and 60 degrees were considered. Hence 5 different models were considered for single lane bridges. The width of bridges was taken as 5 m meters including curbs of 0.225 m width and 0.225 depth provided on both sides. The depth of the slab was taken uniform of 0.750 m. The meshing was kept same as 8 layers of elements across depth, 10 elements along width and 16 elements along span 3. For 4-lane bridges the width was taken equal to full formation width of 19 m including 0.750 m wide curbs provided on both sides. The depth of curbs is taken as 0.3 m. Only single span of 8 m was considered with 5 different skew angles of 0 degrees, 15 degrees, 30 degrees, 45 degrees, and 60 degrees. The thickness of bridge was taken as uniform depth of 0.750 m. The meshing was kept same as 8 layers of elements across depth, 38 elements along width and 16 elements along the span. Different spans and widths were considered to achieve different aspect ratios of length/width. 1.8 Maximum bending stresses. The results for the normal right bridges were checked and were matched with the conventional analysis. The following 3 cases were used for the analysis. A. Self-weight. B. Self-weight and symmetric live loading with respect to the longitudinal axis. C. Self-weight and eccentric live loading with respect to the longitudinal axis. For convenience, the slab has been divided into 5 zones and the maximum stresses developed in those sectors were tabulated, and as the stresses in the top and bottom surfaces were equal they were easily converted into bending moments. C:\users\bhab_desktop/thesis work/n2.png. Fig 7 SKEW slab showing various regions. The following bending stresses were considered for 8M2 lane bridge to find out the maximum design moments. 1 stresses parallel to the central line, parallel to x-axis SX. 2 stresses parallel to supports, SI. 3 stresses perpendicular to supports, senior. 4 principal stresses S3 and S2 given by ANSYS. 1.9 variation of stresses parallel to the central line, so Sx is the stress that developed in the direction of the span length, it is the main design stress in case of right bridges. However, it is not the case with the skew bridges, as we can see there is a decrease in heat stresses with the increase in skew angle. 1.10 variation of the stress parallel to the supporting edges SC. Similarly, the stresses parallel to the supporting edges were also plotted along the central line and mid-span of the 8M21ANE bridge for the 3 different loading conditions. The following figures explain the variation of the stress with increase in the angle of skew. 1.15 Conclusions. The following conclusions are made on basis of above discussion and the results presented in the previous chapter. 1. The effect of skew can be considered as a reducing factor for the maximum sagging moments along the span. The maximum sagging moments decrease with increase in the angle of skew and reduce to about 1/3 of the value at right span. However, there is a development of hogging moments at the obtuse corners of the slab and it increases with the angle of skew. 2. With the increase in the angle of skew there is increase in the moments parallel to the supporting edges, MZ. 3. The maximum principal bending moment, MI, and the moments perpendicular to the supports, MR, follow the same trend as the moments parallel to the span direction, MI, however their magnitudes are higher than the MX values. 4. Torsion stresses is also development at obtuse corners of the slab and it increases with the increase in skew angles and reaches its maximum value at about 40 degrees and then it decreases. 5. The uplifting of the acute corners can be prevented by providing heavy curbs or footpaths along the supports, as no uplifting was observed in the present study. However, there is concentration of shear stresses at supports near to the placement of live loads in bridges of higher skew. There is also increase of reaction forces at the obtuse corners. 6. There is variation of shear stress distribution across the width of the slab, and it increased tremendously at the obtuse corners of the slab. At last, it can be concluded that this analysis has produced results which will be useful to the designers, and also by analysis using 8 noted brick elements in several layers, it can give accurate results for reactions, shears, moments, and torsion. Use of shell elements is simpler and requires less computer time, but it gives accurate results for moments and torsions only, and its shear values are not accurate, hence it has limited use to designers.